हाँ वो मेरा,
हाँ क्या?
वो रोल नंबर मेरा पुराना ही लिया हुआ है उसने,
ओके,
इस वजह से ऐसा दिखाता है।
ठीक है। और अभी तक कितने पेपर्स पब्लिश हो गए?
अभी एक भी नहीं हुआ सर, पहला ही है।
ओके, गुड गुड, ठीक है।
एक्चुअली मेरा इनिशियल ये था, क्या कहते हैं, कोविड से पहले। तो मैं इसी होप में घर नहीं गया था, कोविड में स्पेशल रिक्वेस्ट लेके रुका हुआ था। मुझे लगा कि अगर, क्योंकि उस टाइम हमें पता तो था नहीं सिचुएशन कैसी होगी, तो सर को ये एक्सपेक्टेशन थी कि हो सकता है कुछ इंस्ट्रूमेंट रन करें, अगर स्पीड और पीपीएमएस रन करता रहा तो हमारा काम फिनिश हो जाएगा। लेकिन सब कुछ शट डाउन ही करा दिया गया, तो मैं प्रिपरेशन मेथड के अलावा कुछ कर ही नहीं पाया, तो पूरा वो बेकार हो गया उस टाइम का अभी प्लान था। तो मैं ना तो घर जा पाया और ना ही कुछ हो पाया यहाँ पे। हाँ लेकिन ये है कि थोड़ा सर थे इस प्रकाश सर यहीं पे, तो वो बेनिफिट रहा कि थोड़ा गाइड मिलता रहा।
अच्छा, ठीक है, तो फिर अभी शुरू करते हैं। ठीक है, तो अभी शुरू करो, फिर शुरू करो।
Okay, sir. So today I will give talk on topological material, and especially I will concentrate on Weyl Semimetal because I am working on Weyl Semimetal. और सर अगर कहीं वॉइस ना आए क्लियर तो बता दीजिएगा।
ठीक है, ठीक है।
Okay, so my outline will be like I will give introduction on what is topology and how briefly we can get to know about the topology. Then I will talk about the milestones. I will not tell about all the milestones because there are so many which have given their contribution to go along this path. But I will give the important milestones which were important on the basis of realizing the special materials. Then I will talk about the first topological phase of the matter, quantum Hall insulator, and the effect behind that. Then I will tell about the correspondence between the edge states and the bulk. I will tell the topological materials, different type of topological materials, then how we can get Weyl semimetal from the band insulator, and the characterization techniques with which we can get to know the information if our material have Weyl fermions or the Weyl points in our material. I have not included my whole topic and the material because it's not published yet, but I will tell the motivation why I have selected Husserl alloys especially, and why I have taken ni substitution in my material. That I will tell, so that we will get to know that how we can select a material on our interest basis.
Okay.
So what is topology? So just jumping into the topology, I will tell how symmetry and topology can go along with, and how can we get to know. So both are the symmetry and topology are important whenever we are studying a condensed matter physics. Previously, we were only studying symmetry because it was enough to segregate different type of materials, and it was easy to read a family, study a family who are having the same symmetry or same property. So symmetry is an operation which you operate on a material, and you get the same result. So if you take this figure, this is a mandala. If you rotate this figure by 20 degrees, you will get the same picture. So we have a rotational symmetry in this figure. So on that basis, like a particular symmetry basis, we can make a family of the material, and we can study they have some particular properties which are same. So it is easy to study a particular compound or a materials elements when we have some sort of symmetry. What topology is? Topology, when we deform a system slowly and whatever remains same, that tells us about the topology. So if you take this picture, the football and the bowl, they look very different. Physically, they look very different. They are different in size and shape, but topological point of view, they are same. Similarly, if you take donut and cup, similarly, they are very different in size and shape. They are very different in physical view, but topology point of view, they are same. So what is same? We call genus, or in broad way, we can say that number of holes in the system. So in the first picture, there is no hole. So it is a G is equals to 0. And in the second picture, it's G is equals to 1 because the hole is 1. It's a very rough view to say that the hole is 0. Otherwise, it's a proper quantity which we get from the curvature of the system. So if you want to see the clear picture, you can see we are deforming a cup to a donut through so many phases. Like here we have 5 different steps by which we have got the donut. So if you ask a person, he will tell that every different phase is totally different from the previous one. But on the basis of topology, they are same because we are just deforming them. We are not gluing, we are not stitching, we are not poking, we are not doing such things. We are simply deforming slowly from the cup to the donut. So they are same in topology. Now, what are the milestones are there which have given us a very clear path? So in 1929, Hermann Weyl solved the Dirac equation, and he got a second type of particles, which he said that they are massless particles. And later we call them Weyl fermions on his name. So previously neutrinos were also supposed to be Weyl fermions, but later with some experiments and calculation, we got that neutrinos are massive and they were striked out from the this family. In 1985, Volkov and Pankrotov gave the first idea about the 3D topological insulator. So they proposed first time that we can have 3D topological insulator. Then in 2005, Kane and Milley gave the clear-cut picture of the first 2D topological insulator. And Bernwig and Hughes gave one system also, HGTE and CDTE sandwiched layer. So CDTE, then HGTE, then CDTE, the tri-layer they gave, and they proposed that we can get edge states and we can get the topological behavior from this type of structure. And in 2007, yes, sir.
Sorry, what is CDTE and what was the other one? ZT?
Mercury telluride and cadmium telluride. CDTE and HGTE.
Oh, CD, cadmium telluride.
CD. Cadmium telluride and mercury telluride.
Okay.
So 2006, Banwig and his group gave the theoretical proposed model for that structure. And in 2007, Molenkamp group experimentally proved the same structure, and they got the helical edge states, they got the edge state, they got with the help of experiment, they proved that their material have the edge state property. So now, how did actually started everything? So the first topological phase was actually quantum Hall insulator. So what happens if you confine electrons in a two-dimensional system? They have only 2 degrees of freedom to move in that system. So if you put magnetic field, they will start doing cyclotron motion. In like this, in a circular motion, they will start moving. And due to this motion, now their energy levels are discrete. They are not continuous, rather they are discrete, and we call it Landau levels. So if you see the Landau level picture, you can see that there is a band gap. This band gap looks similar like our insulator band gap. We are also calling it quantum Hall insulator, but will they behave as an insulator, or their behavior will be totally different from the insulator? That we get to know when we did the Hall effect measurement or resistivity measurement in that material. So when we put electric field perpendicular to the magnetic field direction on the plane, the electrons will start moving in a helical path. And when we calculated the conductivity of that material, it was quantized. And the n is the integer number, and the conductivity is multiple of E square by H, and that number n we can calculate with the accuracy of 10 to the power minus 9. So we can calculate with the very accurate value of the n for this type of material. And if you see this picture, that longitudinal conductivity is 0 in some values of magnetic field, and suddenly it's going to be very high. And if you see the transverse resistivity is having plateau. So why we are getting this type of properties are very interesting for this type of materials. And that's how it all started with the quantum Hall effect. That effect was measured in 1980, but the materials based on these properties were get to know very recently, means few decades ago only.
And what is green?
Yes.
And what are the green peaks?
So these are longitudinal resistivity.
Okay. And the red one is?
This red are transverse resistivity.
Okay. Okay.
So how we can connect the age states and the bulk state and how they are different. So Thouless in 1982 gave the theorem, and he told that the conventional insulator and the quantum Hall state, like the quantum Hall insulator, we can distinguish them on the basis of their topological properties, the band structure, the topological properties of the band structure of different materials. And when we have a band gap in our that insulator, quantum Hall insulator, the occupied electronic states and the valence states, if we change the function smoothly on the momentum space, we can classify on the basis of it invariant, topological invariant, which we can calculate with this formula. That n value is actually topological invariant, and on the basis of this value only we were differentiating that cup and donuts are same and football and bowl are same. So we call it integer Chen number or TKNN number on the name of these four scientists, Thouless, Komoto, Nightingale, and Nijs. So on the basis of we are calling them TKNN number. For insulator, N is 0, and with the rest conductivity is multiple of E square by H. So how experimentally? Yes, sir.
Sorry, can you please go back? Yeah. So is this n related to the genus G?
Yes, sir. Actually, that n or this formula is actually if you integrate the curvature of that system now, so you will get a definite integer. Like if you differentiate the curvature of that cup and the football or a cycloid of a different shapes, you will get a particular digit.
Okay.
There is a theorem, Gauss-Bonnet theorem. If you go through that theorem, you will get that whenever we are taking that k curvature 1 upon r1 or r2, the different radius if we are taking of that particular surface. So if in that k, if you integrate, you will get that number n.
Okay. And this equation seems to be some kind of expectation, not exactly expectation value, but since you are dividing by 1 over 2 pi I, so is it some kind of, I mean, I'm just guessing because these kind of equations you see in complex analysis in which you calculate some kind of residues. And so that would be my second question. So my first question is this some kind of expectation value because you are sandwiching some operator x in between nabla k UK, nabla k UK? What is this quantity?
Which quantity, sir?
I mean, so is this some kind of expectation value of x? And what is x here?
This one x?
Yes.
Oh, this one x I will have to go through. I don't know exactly.
Okay. And the same question for UK as well. So what is UK? And then it also seems that the integral will turn out to be complex because you ultimately will have some integer. So
integer,
the integral will also be complex. Okay.
So the inside part should also be complex so that the overall value will be
real. Yeah, integer also. Okay, so and the second one would be, to me, it may not be related to it after all, but the form of the equation suggests that it is some kind of residue of some sort, because if I remember it correctly, you have these kind of factors 1 over 2 pi I when you calculate residues, or you perform some contour integration, and if there are singularities in your area of integration, then the integral is equal to 2 pi I into sum of residues. So perhaps it has something to do with that. I mean, just to give some mathematical insight, just to have some mathematical insight.
Okay.
Do you remember that result?
I remember, but actually this time I haven't gone through that theoretical part now.
Okay.
Because it has a very deep theoretical point of view also. When we solve these equations, we take different structures and we calculate these values.
Okay.
But I will check and I will
Sure.
find out all the things in the next.
And please let us know as well.
Okay.
Sure.
So Halpin first explained that how quantum Hall effect can be explained with the help of chiral states. So he said if we take the A's of the 2D system, like this system, if we do not take the bulk part, we just take the A's of this material. So we can prove we can explain the quantum Hall effect. So if we take the A's only, we can see with the next slide. See, this is the system where we are taking the both areas, the bulk also and the A's also. So whenever we are putting the magnetic field, the electron which are inside the bulk, they can rotate in a full circle, but the electron which are on the A's, they can move only in the half circle. Then they will have to come back to the system because they cannot go out of the material. So this type of motion they will do. So what happens? The electrons which are inside the material, the bulk material, they can scatter, they can means they can scatter from the defect, they can scatter from the other electrons, but the electrons which are on the A's, they are moving in some kind of non-scattering conditions. So they will move only in one direction. So the states, these type of electrons which are at the A's, they will get the A's states, and the speciality of these A's states, like they are topologically protected and they cannot move in the opposite direction, or they will move only in single direction. So the electric current which will flow because of them will be without dissipation, and the conductance is quantized, precisely quantized because of these electronic motions, and they are insensitive to mild disorders. So that's how we will get. Yes, sir.
Sorry, I have a question. So so won't these electrons be, because ultimately these electrons are also for some time at least they are, because not for all the time they are on the edge, for some time they're also inside the bulk. So won't they get scattered with the electrons inside the bulk for some time also? Because
no, one particular electron, if that at the edge, and it will start doing that skipping orbit motion, or it will start skipping. After that, it will not get scattered. Maybe in initially, whatever position it will be, it will start scattering. But as soon as it will reach to the boundary or the edge, after that, it will start doing that skipping orbit, and it will not scatter after that. In the previous situation, it can get scattered whenever it was in bulk.
okay, so and what happens when the electron is at the point in which you have shown the arrows? So won't it be scattered at these points, because it will eventually follow this orbit?
This here?
Yes, here. So what happens here? Won't it be scattered here?
Means according to the definition, they are not going to scatter, because if they will scatter here, ultimately it is happening, scattering is happening, and there is no point of you saying that they will not scatter, they will not do the U-turn, or they will only move in the forward direction.
No, I don't understand.
Means if we are saying that at this position they will scatter from the other electron, so there is no meaning, like I'm saying that they will do a skipping orbit, they will move in the forward direction only. So if they are scattering, then we cannot say these statements. Means I am also in a asking position, like if they are saying that in edge states electrons are moving in a skipping orbit, and they are moving only in forward direction, there is no scattering. It means even in this position they are not getting scattered. Or there is one more thing, like we know that scattering can only happen whenever that scattering length is smaller than that, what do we say, that lambda,
De Broglie?
De Broglie, or what do we call them? They call a particular length, that is scattering length. If that is larger than that, then only scattering can happen. So maybe when they were doing this circular motion, that diameter may be less than that. That's why they are not coming into that picture. That is, scattering is not happening. Maybe.
Okay.
I'm saying.
Okay.
Otherwise, otherwise it cannot happen. If they will also scatter, the chiral edge states cannot be having that a high conductivity or high conductivity.
Okay. And will it also happen? So the electrons that are inside the bulk of the system,
Yes.
they're going round and round. But like what happens to the electrons that are on the edge? So will this happen that, let's say in this plot you have shown that starting from the left top corner, they will move to the right top corner, and
Yes, sir.
and they will have these kind of orbits for all the four edges, and in this way they will also kind of move inside the four edges. Is this the way it happens?
So if this electron we will see now, if
Mhm.
we see this full picture, they will start like this, and then when it will reach here, it will go like this and will start the
Okay.
initial orbit like it was doing before.
Okay.
This electron is moving in opposite direction. This is moving this side and this is moving this side. So if I will show the single electron, it will go around and around and around like that.
Okay.
So what was the problem with such system? The electron which was moving in single direction, the first thing, it was happening in a very high magnetic field, and the second, it was not respecting the time reversal symmetry. If we put the time reversal symmetry, the direction of the motion was getting changed. So in this single system, we are getting one single edge state. This is conduction band and valence band, and this edge state is connecting those two bands. So how can we get rid of, if we put two systems which is having a opposite direction electrons, then it will start respecting the time reversal symmetry, and we will get this type of edge states. So now we are having a time reversal invariant. It is respecting the time reversal symmetry, and where the, like insulator, if we are taking, the conductivity is 0, so it's respecting that also, n is equals to 0. So
Sorry, I have
yes, sir.
one more question. So why do we want to have time reversal symmetry? Because you see, wherever in any equation you will have second derivative of time, so that equation will automatically respect time reversal symmetry. But wherever you have only odd order derivatives, like the first order derivative, third order or fifth order derivative of time, so those equations will not satisfy time reversal symmetry. So my question is, like, why? So I think we see time reversal symmetry being violated in nature. So why do we want it to be respected here?
Actually, like in insulating condition, like if we take topological insulator, or we take our band insulator, even in the direct states also, the time reversal symmetry is preserved. In that particular single situation, when there was a single state and the electrons were moving in a single particular forward direction, here only time reversal symmetry was not preserved. But when we see our already observed systems now, their time reversal symmetry is preserved. Even if I see my Weyl semi-metal materials,
okay,
any of the symmetry can be broken, either the inversion symmetry or the time reversal symmetry. So even my system time reversal symmetry can be broken. They are saying, they are trying to get the similar system where time reversal symmetry is preserved. And if they can prove theoretically that, yeah, in this system the time reversal symmetry is not broken, then they can relate it to their already observed systems.
Because this is
otherwise there are systems already where we are breaking the time reversal symmetry.
But in this case, they find that the symmetry is preserved. This is
in this system it is preserved. Yes.
Okay, sure. So this is an observational fact then.
Yeah, this is observation.
Okay, fine.
So how many types of topological materials are there? There are many topological materials, but I am giving only 3 because that's how we have already divided our materials like insulators, semi-metal, and superconductors. So I will talk about semi-metals. So there are many semi-metals, but mainly 4 semi-metals on the basis of different properties. We divide direct semi-metal, Weyl semi-metal, borderline semi-metal, and triple point semi-metals. So how we can get from our trivial band insulator to topological insulator? So if we can get the band inversion, and with the help of spin orbit coupling, we can open up the gap. Like we are having a band inversion, we are getting 2 crossings. If we open up the gap like that with the spin orbit coupling materials, and in this way we can get the surface states and the special Fermi energy surfaces. And when we go from the trivial insulator to the topological insulator, the particular situation, the particular point where the bands are just touching, at that condition we get Dirac states. So in this state we have some symmetry protection, like inversion symmetry protection is there, time reversal symmetry is preserved. So that symmetry protection we are getting the band touching. So if in this band inversion condition, if we open up the gap, we get topological insulator type condition. If in the just the band touching condition, the symmetry is protected, we get the direct semi-metal condition. If we break one of the symmetry, either inversion symmetry or the time reversal symmetry, we can get the Weyl semi-metal. So in topological insulator, we have a closed Fermi circular surface. But in Weyl semi-metals or direct semi-metals, we are having arcs, Fermi arcs. It's not a closed loop. And these arcs are connected from one surface to the another surface through the bulk. So that's how the surface is connected through the bulk in our direct semi-metal and Weyl semi-metal. And these points which are having opposite chirality, they are actually Weyl points. So from one direct points, you can get 2 Weyl points.
Okay. And
so this is a symmetric. Yes, sir.
And what was C equal to 0 and C equal to 1?
This is actually that surface which is in the vicinity of Weyl points, between Weyl points. That surface has that Chern number 0, and the surface which is out of these Weyl points, that is having that C is equals to which is in between the Weyl point, this is having 1, and the surface which is out of that Weyl point, this is having 0.
And and this is the case for Weyl and Dirac semimetals. And you
Weyl and Dirac semimetal.
And you showed that there are 4. And so the similar kind of thing happens for those 2 cases also.
Which 2 cases, sir?
Because I think you said that there are 4 kind of semimetals. Nodal, I think there was nodal as well.
All of the 4, this will happen. The thing is, they are divided on the properties, like in triple point semi-metal, the bands are not just touching at 2 points, it can touch in 3 points. That's why they are saying triple point semi-metal. So the band touching is happening in 3 points in nodal line. Exactly, I have forgotten that some phase transition, quantum phase transition was happening in nodal and semi-metal. Exactly, I will tell. In direct semi-metal and Weyl semi-metal, they are just the initial differentiation. Like direct semi-metal is having a single band touching, and when with the help of symmetry breaking, you can get 2 Weyl points from the single direct points, whichever having the symmetry protection. So if you see in topological insulator, we are having a Fermi circular surface, but in our Weyl semi-metal and direct semi-metal, we have arcs, and these arcs are actually connected through the bulk, and it is going through the points, Weyl points. So this is a symmetric diagram. So this is a surface contour, and this is a arc. This arc is connecting through these points. These points are actually a projection from the bulk. So this is the insulator. When we are getting a critical point, if we break any symmetry, we can get two Weyl points from one Dirac points, and these points have opposite chirality or the charge, and we can get such type of picture for our Weyl semimetal. So how we can disturb a Dirac phase and we can get the Weyl phase? So I told you there are two conditions. Either we can break the inversion symmetry, or we can break the time reversal symmetry. If we break the inversion symmetry, we can simply take a system or like a crystal structure which is having a non-centrosymmetric structure, or if we incorporate a magnetic impurity or we substitute some magnetic system, we can break the time reversal symmetry, or a high spin orbit coupling material. If we dope, we can break the time reversal symmetry. So in these two ways, we can get the Weyl semimetal. So there are many characterization techniques, and theoretically, if we study the surface plasmon polydetons, the dispersion and the disappearance of the particular wave function can get you an idea about the presence of the Weyl fermions. And experimentally, the RPS is the best experiment. You can get directly the picture of the surface states, surface arcs, notice, and as well as the Weyl points. Otherwise, you can take the help of scanning tunneling microscopy. With the help of DFT calculation, you can also get exact idea about the Weyl fermions. Otherwise, if you don't have these experiments facilities, you can also get indirect experiments, and you can get the idea. You can do the transport measurement. You calculate the SDS Subnikov-Dehas oscillations if you do Hikami-Larkin fit, and if you are getting the alpha and I5 values related to the theoretical calculations, you can get the idea. So what is RPS? This is the RPS picture of TAAS material. So this picture, we can see these dark red lines are actually Fermi arcs, and these maybe white and black points are not that much visible. This is black point, this is white point. These are Weyl points. Here you can see this and this. These are Weyl points from the bulk, and these red lines are from the surface arcs. So from the RPS, you can see the exact picture of arcs as well as the Weyl points. This is a symmetric diagram. So there are so many Weyl points. This means generally it is a inversion broken symmetry. So when in our material inversion symmetry is broken, most of the time we have multiple Weyl points. We have many number of Weyl points. And if we are having a time reversal symmetry breaking, number of Weyl points are less. So Jahid and Hassan group has done this experiment. And how this experiment is useful: if you take low energy photons, you will get the surface information, and if you will get high energy photons, they will penetrate the surface and they will give the information about the bulk of your system. You can do STM measurement also. So STM will give you the mapping of the conductance of the tip and the material. So the picture will look like something like this. If you do the fast Fourier transformation, you will get the arc information about the arc. But with STM, you cannot get the exact information from the bulk. So if you do the DFT calculation, if you do the band calculation, you can get the points, the location of the Weyl points, and you combine the information from your STM measurement and the theory calculation, then you can get the full picture that you can do with the help of STM. Otherwise, you do the conductivity measurement in if rho versus H, you are getting oscillations like that. You can say that yes, I am having conducting surface states, and how Sumnikov-Dehas effect works actually. So if you see this picture, this is on the when magnetic field is 0, we are having a continuous energy spectrum. When we have magnetic field, we will get Landau levels. So why these oscillations are happening? This peak means the resistivity is suddenly increasing, then suddenly it is decreasing. So these peaks means a condition where resistivity is suddenly decreased. So when resistivity will decrease, if Landau level is fully empty or it will fully filled, in these two conditions the resistivity is minimized. But when the Landau level is uh, in half field, the scattering will be very high and the resistivity will increase suddenly. So these conditions where you are getting a peak, it means the Landau level is partially filled. So what happens when you will increase the magnetic field, slowly the Landau level will broaden and it will cross the Fermi level, and you may get these different type of situations again and again, and that's why you will see oscillation in your resistivity data. So if you will get the Subnikov-Dehas oscillation in your material, you can say that yes, you may have surface states and you are getting Landau levels in your material. And the other is Ikami-Larkin fitting. In Ikami-Larkin fitting, it will tell about what type of localization in your material is there. You are having a weak anti-localization or weak localization or a combination of that. So in fit, if you will get the alpha value 0, it means you are having a strong magnetic scattering. You are not having any WL or WAL condition. But if the value is 1, you are having a spin orbit interaction and it is weak. The magnetic scattering is also weak, the spin orbit interaction is weak. If it is 0.5, then spin orbit interaction is strong and you are having conducting surface states and you are having weak anti-localization. And if the value is in between from 0.5 to 1.5, you can have combination of weak anti-localization and weak localization. And with the help of phase coherence length also, you can guess that what type of situation in your picture is. So in my, this is the fitting from my sample. So my HLN fitting is exactly matching at low temperature from the with the experimental data. So I'm getting alpha 0.48 and I 5:75. So my value is close to 0.5. So I am getting the weak anti-localization, and I can say that my sample has conducting surface state. So yes, sir.
Sorry, but your alpha is minus 0.48.
Yes, sir. Oh,
So it is not matching with any of these. I mean, so the last one is from 0. Oh, yes, it's
no,
was in
sir,
the last
no,
one.
actually, no, sir. Actually, here I have missed minus sign.
Okay, fine.
Here I haven't put minus sign. Minus sign was there.
Okay. And one more thing, is this fit? Ikami-Larkin Nagoaka fit? Is this phenomenological, yes, or can you derive it using some fundamental physics?
Sir, we can derive it actually. They have derived a very cumbersome theoretical calculation is there. I have the paper of Ikami.
Okay.
And
because I mean, yes, never I have seen di gamma function coming anywhere in. I mean, I've not seen it anywhere, because di gamma is the derivative of the gamma function, first derivative, or you can take any number of derivatives. But I think the di gamma function is the first derivative of the gamma function.
Okay. Actually, I gone through that paper, but it was so theoretical. There was a full calculation of this equation. There is a 2-page calculation. Then we will get this equation. So they are getting this equation from our journal physics only. They are putting so many conditions and they are getting.
Fine. Is it P? Oh no. Progress of theoretical physics. It's Oxford University. Oxford University.
Means Oxford University, this paper?
No. Progress of theoretical physics, Oxford University का journal है.
अच्छा, okay.
Oxford publications है Oxford University का journal.
Okay. So I have done HLN fitting and I am getting Sumnikov-Dehas oscillations also in my conducting, in my transport measurement. So with these two help only, I am saying that my material has conducting surface states.
Oh.
So while semi-metals are so interesting nowadays, because these are the materials only which we are giving the realization of Weyl fermions in all the physics, and they are only spread the field of topological materials from the insulators, because initially only topological insulators were very studied in its thorough way, and they host the Fermi axis surface state, which gives so many new characteristics of the material, and they are having chiral anomaly, and the surface to bulk correspondence gives different type of properties to our materials also. So why in my materials, my sample is Usler alloy. So zirconium based Usler alloy. So why I have selected Usler materials? Because already Usler compounds have particular properties, like they have thermoelectric properties, magnetocaloric effect, and they have half metallicity. One channel is having a particular spin polarization. And if we see the future plan, and if we want a device fabrication in Usler material, you have very variety of materials, and the lattice matching for is very easy for Usler alloys. The second thing is, in my material, the time reversal symmetry is broken. My crystal structure is centrosymmetry. So the number of Weyl points are less. In my material, only 2 Weyl points are there. So if in future I want a modeling is easier for my material, or the material which are having less Weyl points. The third point is, Usler alloys most of the time have very high Curie temperature. My material has 455K. The parent sample have 455K. And Ni substitution I did in my material because cobalt is there, and in theoretical approach, people have shown that if Fermi level is close to the Weyl node, the surface properties increases, the conduction surface properties will increase, and with the help of secondary experiments also, you can prove that Weyl fermions are there. So I doped Ni because Ni has one more valence electron rather than cobalt. So I was hoping that Fermi energy or the Fermi level will go close to the Weyl. That's why I did Ni substitution. So thank you.
Okay.
This was the talk for today.
Thank you for the talk.
Thank you, sir.
Can you please go back to the previous slide?
Yes, sir.
Okay. Oh, yes. So, I mean, maybe the question is not that useful to ask, but still, as you said, because when you have time reversal symmetry, you will have lesser number of Weyl points, but when you have the inversion symmetry, then you will have more number of. So, is there a way of quantifying it? Because
actually, in very broad way, I can tell that whenever inversion symmetry is breaking, what should I say, to neutralize the chiral charge, the number of Weyl points will be more. Like if we have a particular situation where we are having Weyl points, generally I have seen, means whenever they are having a inversion symmetry breaking now, to make the chiral charge zero, the total chiral charge zero, the number of Weyl points are increasing in that system. Okay. But whenever the time reversal symmetry is breaking, there is no interference or there is no disturbance in the chiral charge. Means, okay, as I have studied in the different papers.
Okay.
And even I have seen also, like not only in my system, in other system also, whenever the time reversal symmetry is breaking, maximum 4 or 4 generally I have seen Weyl points. Maybe there are more also. But in time inversion symmetry breaking, now like TAS, sometime there are 16 or 18 Weyl points are there. There are multiple Weyl points are there.
Okay.
So when they are doing the theoretical modeling, now it is very difficult for them to model their system.
No, so then my question is the number of Weyl points given that given, let's say, the time reversal symmetry or the inversion symmetry is broken, can we a priori say that this will be the number of these points that will be found finally? Can we say something like that?
सर मैं क्वेश्चन समझा नहीं एक्चुअली.
मैं पूछ रहा हूँ कि जैसे ये जो नंबर ऑफ ये वाले पॉइंट्स हैं, जो Weyl पॉइंट्स हैं, कैन वी प्रिडिक्ट देम अ प्रायोरी कि जैसे ये वाले मटेरियल में देयर विल बी दीज मेनी नंबर ऑफ पॉइंट्स गिवन टाइम रिवर्सल सिमेट्री या फिर इन्वर्जन सिमेट्री हैज बीन ब्रोकन, और मतलब तो और इन अदर वर्ड्स कि मतलब क्या ये केवल उस पे ही डिपेंड करता है कि सिमेट्री ब्रेक हो, या फिर मतलब कुछ और प्रॉपर्टीज पे भी डिपेंड करता है?
नहीं सर, सिर्फ इस पे डिपेंड नहीं करता. मतलब ये एक तरीके से पॉजिटिव आउटकम है, जैसे मतलब कि हाँ अगर ये सिमेट्री ब्रेकिंग है तो ये कम होंगे या इनकी क्वांटिटी कम होगी, बट सिर्फ इस बेसिस पे वो कैलकुलेट नहीं करते कि ये टाइम रिवर्सल ब्रेकिंग है तो इसमें 2 या 4 होंगे, अदरवाइज उसमें है तो इतने होंगे, ऐसा नहीं। ये थ्योरेटिकल कैलकुलेशन ही है, या मतलब वो कैसे कैलकुलेट करते हैं एग्जैक्टली मैं नहीं बता सकता कि हाउ दे आर प्रिडिक्टिंग और व्हाई दे आर कैलकुलेटिंग दैट दैट मेनी वाइल्ड पॉइंट्स आर देयर, बट मैं सिर्फ एक कॉन्सिक्वेंस बता रहा हूँ कि जनरली टाइम रिवर्सल ब्रेकिंग में नंबर ऑफ वाइल्ड पॉइंट्स कम होते हैं रादर देन इनवर्जर सिमेट्री ब्रेकिंग।
मतलब कैन वी वर्क दिस आउट, मतलब मैं बोल रहा हूँ कि अगर ये वर्कआउट नहीं कर रखा है तो अगर मुझे थोड़ा बैकग्राउंड पता चले तो मे बी वी कैन वर्क दिस आउट कि कितने होंगे।
कर सकते हैं, ये तो है कि हम अगर हम थ्योरेटिकल कैलकुलेशन।
अब आवाज नहीं आ रही है निखिल, आवाज नहीं आ रही है।
हेलो।
हाँ अब वापस आ गई, ठीक है।
हाँ मैं कह रहा हूँ सर कर सकते हैं, कैलकुलेट कर सकते हैं, बट मैंने उस तरफ अभी ऐसा गया नहीं हूँ कि मैं कैलकुलेट करूँ वाइल्ड पॉइंट्स कितने हैं, क्योंकि जो मेरा पेरेंट सैंपल है वो ऑलरेडी प्रिडिक्टेड है, उस पे 2-3 पेपर ऑलरेडी आ चुके हैं, सो दे हैव ऑलरेडी कैलकुलेटेड देम। सो अगर मैं उन्हें कैलकुलेट भी करता हूँ तो मुझे कोई नया रिजल्ट नहीं मिलने वाला था, इसलिए मैं उस साइड अभी इतना गया नहीं। तो मैंने अभी सिर्फ उसमें इफेक्ट ऑफ द सब्स्टिट्यूशन ही मैंने सिर्फ स्टडी किया है।
हाँ मतलब मेरा क्वेश्चन तो ये था कि जैसे कि
कर सकते हैं या नहीं कर सकते।
हाँ मतलब जैसे पहले से कोई कि गिवन की कोई मटेरियल जो हमने पहले से प्रिपेयर नहीं किया है तो
हाँ
एक्सपेरिमेंट करने के बाद तो पता चल ही जाएगा कि कितने होंगे, लेकिन एक्सपेरिमेंट करने से पहले गिवन।
पहले, हाँ सर कर सकते हैं, कर सकते हैं। वो जितनों ने भी थ्योरेटिकली प्रिडिक्ट किया है दे ऑलरेडी टेल दैट दैट मेनी वाइल्ड पॉइंट्स विल बी देयर और कैन बी देयर।
ओके ओके ओके, ठीक है ठीक है, ओके थैंक यू, ठीक है। तो किसी और की कोई क्वेश्चन है?
मैम के पास ही क्वेश्चन हो सकता है और कोई तो है ही नहीं यहाँ पे।
नहीं एक्चुअली मेरे पास क्वेश्चन नहीं है, मैं थोड़ा समझने की कोशिश कर रही थी।
अच्छा अच्छा ओके।
ओके तो ठीक है।
हाँ प्रकाश सर होते तो वो क्वेश्चन पूछते क्योंकि उन्हें ये फील्ड बहुत पसंद।
हाँ सही बात है। नहीं और वो मुझे कुछ बताते भी रहते हैं इस बारे में।
अच्छा अच्छा हाँ।
तो मुझे
वो भी
कुछ
काम भी
नॉलेज है
कर रहे
इसके
हैं ना
बारे
इसी फील्ड में।
में। मुझे थोड़ा बहुत नॉलेज भी है। ओके तो
हाँ
ठीक है।
उन्हें एक्चुअली कोरोना में सिर्फ इतना ही पॉजिटिव हुआ कि वो मेरे साथ थे यहाँ पे और उन्हें फील्ड बहुत पसंद थी, तो वही पढ़ाते रहते थे मुझे, क्योंकि मेरे सर के लिए भी ये बहुत नई फील्ड है, उन्होंने नहीं स्टडी किया है इसे। तो वो भी हमेशा टॉक होती है तो प्रकाश सर से ही बोलते हैं कि तुम ही क्वेश्चन पूछो। हाँ क्योंकि उनको भी इतना वो नहीं है इसमें, क्योंकि इसमें
हाँ
थ्योरी पार्ट बहुत ज्यादा है, मुझे इसीलिए डिफिकल्टी होती है क्योंकि मैं थ्योरी में इतना अच्छा नहीं था, मुझे अभी पढ़ना पड़ता है थ्योरी।
हाँ हाँ मतलब कि यदि कुछ ऐसा है कि जैसे हम अगर अब अगर मुझे थोड़ा बैकग्राउंड हो और कुछ ऐसा है कि मैं थियोरेटिकल एस्पेक्ट की बोल रहा हूँ, पता नहीं मैं एक्सपेरिमेंट तो मैं कितना कंट्रीब्यूट कर पाऊंगा, लेकिन मैं बोल रहा हूँ
हाँ
कि
हाँ
अगर कोई सा थियोरेटिकल एस्पेक्ट है तो फिर हम तीनों वर्कआउट कर सकते हैं अगर वो पहले से वर्कड आउट नहीं है तो। मतलब ये एक पॉसिबल प्रोजेक्ट
हाँ
हो सकता है।
कर सकते हैं पॉसिबल, हाँ बिल्कुल हो सकता है। और
नहीं
वो
है मेरे लिए
बेनिफिशियल
पॉसिबल।
भी होगा मेरे लिए भी। और
हाँ मतलब मुझे भी कुछ
आप,
कैलकुलेशंस डिराकी क्वेश्चन के, या मतलब मुझे वो इतना अच्छे से आता नहीं तो मुझे समझ में भी आता है।
हाँ कुछ नया हो जाएगा ये तो है।
हम्म, ठीक है। हाँ ठीक है, मतलब यदि ऐसा है कि आप दोनों जब डिस्कशन करें और अगर ऐसा लगे
हाँ
कि
हाँ
तो मतलब ये एक विएबल एक पॉसिबिलिटी है कि ऐसा कुछ काम मिलके कर सकते हैं।
कर सकते हैं ये तो। एक्चुअली आप भास्करन सर को जानते हैं क्या सर?